Hello and welcome to non-IIT. So we have essentially discussed a lot of things about group theory till now. In the previous lecture, we were discussing about the symmetric groups, alternating groups, and the dihedral groups. Now, in this particular lecture, our main goal will be to discuss a few more facts about homomorphisms, but specifically uh, more focusing on how to count homomorphisms between two groups, which is an essential branch from which questions usually come in the competitive exams. So this lecture will be highly important for everyone who are preparing for IIT JAM and similar kind of competitive exams in mathematics. So without further ado, let's start. So what we are going to talk about is the notion of counting homomorphisms, and that will be our primary goal for this lecture. And the essential idea behind counting homomorphisms is the first theorem of isomorphism, which we had discussed in some previous lectures. So let us give a quick recall. So recall first theorem on isomorphisms. And the first theorem of isomorphisms basically speaks of the following typical thing. So let phi from a group G to a group H be a homomorphism, then the quotient group G mod kernel of phi, this is isomorphic to the image of phi, which is a subgroup of H. More specifically, what we can say is in the following sense, that G mod kernel of phi is embedded in H, that is, it is isomorphic to a subgroup of H. And furthermore, if phi is surjective, which is quite obviously observable, then the quotient group G mod kernel of phi will be isomorphic to the whole group H. So this is not exactly the first theorem of isomorphism. So the first theorem of isomorphism typically ends here, and the later portions are quite immediate observations from the first theorem of isomorphism. And let us first produce what is the algorithm for counting homomorphism from a group G to a group H. So please focus on this particular thing. So the algorithm for counting homomorphisms from a group G to a group H. Okay, yeah, fine. So let us produce the algorithm one by one, and let us primarily focus on what we are trying to do. So the first thing which you would like to do is that find the normal subgroups K, or let's say Ki, I equals 1 to n of G. Okay. Number 2, what you want to do is that you will set let's say Gi to be the quotient G mod Ki. Now why actually we are trying to do this? So let me give you a very brief background of what we are actually trying to do. Observe that every normal subgroup of a group G is the kernel of some homomorphism, and we already know that the kernel of some homomorphism is actually a normal subgroup. But the other way around is quite typically from the fact is that if you take the natural projection of G to G mod n, where n is a normal subgroup of G, then you can observe that the kernel, so how this map is defined is basically you take an element G and you simply map it to its coset. And what you can observe from here is that the kernel of pi is exactly n. So there exists a homomorphism corresponding to every normal subgroup such that the kernel of that homomorphism is exactly that normal subgroup. So there is a 1-1 correspondence between kernels of homomorphisms and normal subgroups in a group. And the reason why we are trying to identify all these normal subgroups is that each of these normal subgroups will give rise to some homomorphism phi such that G mod kernel of phi will be isomorphic to some subgroup of H in some sense. I hope you're getting what I'm actually trying to do. Okay, so I hope it's clear. And then what we will be doing is that, so this must be, so our background, let me again give to the background. So this must be isomorphic, or at least we want it to be isomorphic to some subgroup, let's say G prime of H. Okay, so for that what we need to do, we need to get hold of all the subgroups of H. Okay, so identify G mod Ki with subgroups of H and say it's Hi. Now obviously not all quotients will be isomorphic to subgroups, every possible subgroup of the codomain group, because this might be possible that some quotient comes out to be cyclic, but probably you will get hold of a group where the corresponding subgroup won't be cyclic. Things in some sense, I'm not being able to get hold of something immediately, but we will come to examples and we'll see that what I'm actually trying to speak of. So number 4 is that the number of homomorphisms from G to H such that this Ki is equal to the kernel should be exactly equal to the, so let this be I is equal to 1 to m. So exactly is the number of such subgroups which you were able to identify using the quotient groups G mod Ki times all possible permutations of those particular subgroups, because if it's an isomorphism, if you're taking G mod Ki isomorphically to Hi, then that should be subdued by all the automorphisms, all the permutations of the elements within Hi. So that should be the case. I hope it's clear. So this gives you typically the number of homomorphisms from G to H with obviously with kernel Ki. So in some sense, so step 5, the number of homomorphisms, total number of homomorphisms, I would like to say total number of homomorphisms equals summation of all these possible elements, so times the order of automorphisms of Hi and whatever number of things you have got. Okay, so you can just take I here as well. Clear? Fine. So let us give a quick example to analyze what we have already done. Okay, so for example, let us take a very interesting example. Find, in fact we are going to explicitly do this, so find all group homomorphisms from Q8, so Q8 to A4. Now before that, let me give you a brief notion of what Q8 is. It's a very interesting group. I have missed discussing Q8 in the previous lecture. This is a good time we do this. So this is called a quaternion group. So this is called the quaternion group Q8, and it consists of the elements 1 minus 1, I minus I, j minus j, k and minus k with the following operations. So the operations are defined in the following sense. See, the operations on 1 and minus 1 are, we are going to define the operation multiplicatively. So anything which happens with 1 and minus 1 will be automatically the same. So I can write as a times 1 is equal to a is equal to 1 times a. So 1 is the identity here. A times minus 1 is same as minus 1 times a is equal to minus a here. Okay, and here minus, please do not attach any additive consequence to minus in this particular case, because the significance of minus doesn't hold additively at this point. Okay, typically the structure of this group has actually come out from actually the quaternion ring. So the rings came into existence first. I hope, and probably you might, whoever is listening to this particular lecture probably doesn't know what a ring is at this point, but once you get into ring, you'll see that there are what we call quaternion rings, and rings also have an underlying group structure. So typically those do not get attached so easily. Okay, so when I start speaking, it gets complicated, I'm sorry for that, but typically the quaternion rings came first into existence, and from there we derived the notion of a quaternion group. Nevertheless, the main thing is how to multiply these ijk. So for that you can just take hold of the cyclic structures. These are typically, you can think of them being vectors in the complex plane. So these represent things like this. So k here, and so the cyclic structure. So I'm just writing one of them. So as you go along the arrow, you get the next element. So you have ij to be k, jk to be I, and ki to be j, and opposite to arrow you get a minus sign. So it's not a commutative group, you get a minus sign. So this minus actually indicates a direction here. Okay, moreover, you have I squared equal to minus 1, j squared equal to minus 1, and k squared equal to minus 1. So these vectors are actually what we call quaternion vectors. So these are generalized these are generalized versions of the imaginary number iota. Nevertheless, what's important about this particular group is the following thing, that is, this group is not abelian. So what we have already seen, that this group is not abelian, but now we already know this very important property of an abelian group, which is quite intrinsic in its own nature, is that every subgroup of an abelian group is normal due to commutativity, obviously. But this is one particular group which is not abelian, but every non-trivial subgroup, or I should rightly say every non-proper subgroup, every proper subgroup of Q8 is normal. So you can actually draw a lattice of these subgroups, and this is how we usually draw a lattice. So you have Q8, then you have these four fundamental subgroups. So you have I minus I, which is I minus I, which is nothing but the cyclic group generated by I. Then you have the cyclic group generated by J, and then you have the cyclic group generated by K, and I hope you will be able to write each of these subgroups. So the cyclic group generated by J will be just 1 minus 1 J minus J, and that of K will be 1 minus 1 K minus K. And all the three essentially contains the subgroup generated by minus 1, which is nothing but 1 and minus 1, and this contains the subgroup generated by 1. So this is how we draw the lattice of subgroups. Okay. Now the one more funny thing about this subgroup is that you can also see that this group is not abelian, but every proper subgroup of Q8 is normal. In fact, all of them are cyclic as well. All of them are cyclic as well. And this actually works as a counter example. So you might have seen, if you're doing the PYQs, at some point you will be seeing that many of the times the question has been asked that there exists a non-abelian group with every proper subgroup being cyclic, true or false type of questions. Nevertheless, having the notion of the structure of these groups, let us move on to how to count the homomorphisms. So our question was find all group homomorphisms from Q8 to A4, and let us check it now. So solution. So what are the normal subgroups of Q8? So normal subgroups of Q8 are, so let us just denote as we had devised the symbol. So K1 to be the trivial subgroup. Let us take K2 to be the cyclic subgroup generated by -1. Let us take K3 to be the cyclic subgroup generated by I. K4 to be the cyclic subgroup generated by J. And K5 to be the cyclic subgroup generated by K. And finally, K6 is the whole group Q8. So now what do we need to do? We need to identify, so the quotient. So let G1 should be G mod K1, where G is just the whole group Q, okay, so equal to G. So which should be just exactly isomorphic to G itself. Then you have G2, which is isomorphic to, so we need to take G2 to be G mod K2, which is so it's Q8 mod 1 minus 1, so it should be a group of order 4, right? So it's either the cyclic group Z4 or it's the cyclic group or it's the Klein 4 group. So this is a very simple exercise. So this is actually isomorphic to K4, or probably I have written it as V4, so whatever it works. So it's a Klein 4 group. This is a very simple exercise. You can check that this is not the cyclic group of order 4, it's actually the Klein 4 group. Then you have G3 to be the G mod K3, but then K3 has order 4, so, and G has order 8, so it's a group of order 2, and every group of order 2 will be just the cyclic group of order 2, so it's isomorphic to Z2. And the same happens for all the others. So G4, which is G mod K4, is also isomorphic to Z2. Then you have G5, which is G mod K5. This is also isomorphic to Z2. And finally, you have G6, which is G mod K6. And this is isomorphic to the trivial group 1, which contains only the identity and nothing else. And now we need to check that what are the possibilities. So one, so we need to check whether there are some subgroups of A4 which can be identified by the quotient G1. So what is the order of G1? So the order of G1 is 8, right? And the order of A4, if you remember, it should be 4 factorial over 2, which is 12. Now observe that the order of G1 does not divide the order of A4. So by Lagrange's theorem, there cannot exist a subgroup H of A4 such that G1 is isomorphic to H. Otherwise, if it's isomorphic to H, the order of H would be same as the order of G1, which is 8, but 8 does not divide 12. So this can't be true. So this case can't be true. So you got an example of when the case fails. So now check the cardinality of G2. So it's 4. So we need to identify that how many subgroups are there in the alternating group A4 of order 4. Okay, now this is a very interesting result that A4 has only one subgroup of order 4, which is exactly Klein 4 group itself. Now if it would have come out to be the cyclic group of order 4, then also this case would have failed, but it's exactly comes out to be, so which is exactly K4. So therefore G2 is isomorphic to a subgroup which is actually isomorphic to K4 in A4, right? So what is M here? So M was the number of subgroups which exists being isomorphic to Gi. So therefore here M is equal to 1. And then what is the order of the automorphism group of K4? So the automorphism group of K4 is actually 6. So total number of homomorphisms here, total number of homomorphisms is equal to 1 into 6, which is 6. Let's move on to case 3. So here you have G3, which is so it was isomorphic to Z2. Yeah, it was isomorphic to Z2. Now, so in case of G3, you need to identify that how many subgroups are there in A4. So how many cyclic subgroups of order 2 are there in A4, and this can actually be found in the following sense, and you can also generalize this, that how many cyclic subgroups of order n are there in A4. That would come out to be number of elements of order n divided by phi of n. Oh, sorry, number of elements. Yeah, so this is the general case. So this is the general case. So here you have this to be the number of elements. Sorry, so the number of elements of order 2 divided by phi of 2. But phi of 2 is 1, right? So it's just the number of elements of order 2. So I need to find what are the possible number of elements of order 2 in A4. So let us just count what are the possible number of elements of order 2 in S4, and then we'll check that which of them are even permutations, and we are done. So how to calculate what are the number of elements of order 2 in S4? So you need to get hold of the cyclic decompositions. Now in S4, possible cycle decompositions giving order 2 is, so what are the possible cyclic decompositions? It should be 2, 1, 1. You need to have at least 1, 2, and you cannot have an element which is prime to 2, or you can have 2 2s. So 2 2s. But which of them are even permutations? So here you have only one transpositions, that is an odd number of transpositions. So this is an odd permutation, but this is an even permutation. You have 2 transpositions. So the only possible cycle decomposition of this form. So therefore number of such elements. So recall how to calculate number of such elements. So this should be just 4 factorial divided by 2 squared into 2 factorial, which comes out to be 4 factorial over 4 into 2, which is just 3. So there are 3 elements of order 2 in A4. So therefore number of homomorphisms, this should be exactly equal to 3 times the order of the automorphism group of Z2. But the automorphism group of Zn is isomorphic to Un, which has order phi of n again. So this is just 3 itself. And the same thing holds for both G4 and G5 as well. So the same holds for G4 and G5. And case 6 is trivial, right? So G6 is isomorphic to the trivial group. So there is only one trivial group, obviously, in A4. So that accounts for only one permutation. That's good of the trivial homomorphism. So only one homomorphism. So total number of homomorphisms. Total number of homomorphisms equal to, so in the first case we had got none, so 0, plus in the second case probably what we had got 6. Then we have got 3 cases of 3s and 1. So it's 9 plus 6, 15 and 1, 16. So the answer is 16. Okay. So I'm giving a very simple exercise which can be probably done by whatever we did here itself. So it's an easier version. Count the number of homomorphisms from, let's say, yeah, we can do it from Q8 to S4. Yeah, do it. So this will be an easy exercise for you, because we have already done the hard work of finding out all normal subgroups and finding out all typical elements there, etc. and etc. Yeah, let us do one more typical exercise. This will also be quite helpful. Let me think of it once. Yeah, so another example, let's say, yeah, count the number of homomorphisms from, let's say, what should I try at this point? I'm thinking of a good example. I do not want to get hold of examples which are not useful. I want to think of an example which is quite easy. I mean, I'm quite good to do. Okay, this is a very interesting result. Okay, so let us think of this. Count the number of homomorphisms from Zn to Zm. Okay, let's try. So solution. Now we actually need not do much a thing here. Okay, because what we can do is that we can go with a very easy observation. See, dealing with homomorphisms on cyclic groups are actually quite easy, because you know that the image of a homomorphism of a cyclic group is a cyclic group, because you will take the image of the generator to a generator itself. You can easily check this out. So each homomorphism is identified by where it takes 1, where we are taking the trivial generator, where Zn is simply generated by 1. Now something which you can try and do is observe that the order of the image of an element under a homomorphism divides the order of the element itself. Okay, so now if f from Zn to Zm is a homomorphism, then the order of f of 1 will surely divide the order of 1. Okay, and what is the order of 1? So the order of 1 is n, exactly n, right? I hope it's clear. Yeah, so what we do is that we give a detailed proof of the thing. So let us actually claim this. So, and I will be using a stronger notation, so I won't be using this layman notation. So claim, so I will be claiming that the cardinality of the number of homomorphisms from Zn to Zm is actually the GCD of n and m, which I typically write just as nm. So we are going to get to a detailed proof of this. So proof. Okay, so let us kind of start with the homomorphism and see what actually happens. So let phi from Zn to Zm be a homomorphism, and let So I am actually denoting these with stronger notation so that you are not confused. Be the generator of Zn. Okay. Now, as I was saying that everything will be characterized by what is the image of this generator. Now, so let the image of this generator be some residue class in M. Okay. And obviously, K will be some element from 0 to M minus 1. Right. Now, what we know is that phi of any element from the residue class Zn, this is nothing but phi of the generator times x. So this should be exactly equal to x times the image of the generator. So this should be exactly equal to k times the image which we have denoted in some sense. So this should be exactly x into k mod m. So this actually represents mod m, nothing else. Now what do we need for phi to be a well-defined homomorphism? Now firstly n times the generator must be 0, right, by Lagrange's theorem. So if I take the image of this, what do I get? So I get n times this should be equal to phi of 0, which is 0, or typically the 0 of m, I should specifically mention. So therefore n times phi of 1 is exactly the 0. So this means that the residue class of n times k mod m is exactly equal to the residue class of 0 mod m, which translates to the fact that n times k is congruent to 0 mod m. Okay, so what do I actually need to check? I need to check what are all the possible values of k such that this happens. So therefore our proof boils down to find all possible k's such that n times k is congruent to 0 mod m. And obviously I need to choose k from where k is an element from 0 1 till m minus 1, and that's what we need to do. Okay, now observe that now if d is chosen to be the GCD of n and m, then I can write, so since it's a common divisor of n and m, so I can write n as let's say some n prime times d, and I can write m as some m prime times d with the GCD of n prime and m prime be 1, because it's the greatest common divisor, so I cannot have more common divisors. So therefore hence I have n prime d times k congruent to 0 modulo m prime d. Okay, but what do I have from here? Let us think a bit. So what do I have? Yeah, so from here I can say that this implies that n prime k is congruent to 0 mod m prime. So this follows from number theory, that is a times k congruent to 0 mod m is same as a congruent to 0 mod m by k, or at least reducing via the GCD. Okay, now since n prime and m prime is has their GCDs to be 1, and m prime divides n prime times k, so by Euclid's lemma, see how much number theory is actually involved in typical algebra. What do I have? I have m prime dividing k. Getting my point? So therefore I need to find all those values which are divisible by m prime, and these are just 0 m prime 2 m prime till d minus 1 times m prime. Is it clear? And how many such values are there? And there are exactly d values. Is it clear? So that's exactly what we require to prove. So go through the proof again, and if there is something which you are being unable to understand, please carefully do the proof on your own and use this the way I proved it as a reference. Or if you have some other idea of proving out these particular things, you can use that too. Okay, sir, and this is a very important result as well. Okay, this is a very important result as well. Fine. Now let us give us a few number of highly important results regarding regarding counting homomorphism. So important results, and each in the case of each of these results, you can actually use the algorithm of counting groups and other properties of subgroups and normal subgroups you already know, or you are curious enough to find out in each of the possible groups. So one of the results we have already proved. So result number 1. So let G be an infinite cyclic group, and let's say G prime is any finite group of order m, then the number of homomorphisms from G to G prime equals m, and the number of onto homomorphisms from G to G prime is equal to 0 if G prime is not cyclic, which is quite obviously observable, and it's exactly equal to phi of m if G prime is cyclic, because in that case you need to find out the specific orders of the elements, and there will be phi m generators. That is exactly the thing. And obviously there cannot be an into homomorphism or an injective homomorphism here, because the domain group is larger than the codomain group. Number 2, so this let me just think of something. Yeah, I can typically try and do this particular thing. Should I give this a result or not? Okay, so the number of homomorphisms from the Klein 4 group to Zm, this is 4 if m is even and 1 if m is odd. And then the number of onto homomorphisms from K4 to Zm, this comes out to be 1 if m equals to 1, 3 if m equals to 2, and 0 otherwise. And there exists no injective homomorphism. There does not exist an injective homomorphism from K4 to Zm. 0. Okay. Now giving a few exercises. So exercise, find find the number of homomorphisms between the following groups. Okay, so number 1, let's take A4, so A4 to Z6, okay, and the answer here should be probably 3. I might be wrong, but probably it will be 3. Then you can do it for let's say K4 to Q8. The answer here will be 4. Number 3, K4 to S4, and this is a huge answer. It's 52. Okay, just try it out. Number 4, let's take an for any n to K4, where specifically n is greater than or equal to 4, and I won't give the answer here. And number 5, let's say from Zn cross Zk to Zm cross Zl, and the answer here, so that you actually will be able to prove this out, or at least I would want you to prove this out. And the answer here is GCD of n and m times the GCD of n and l times the GCD of m and k times the GCD of k and l. And once you have a proof of this, you can also take this as a fact if you ever find it difficult to prove this. But you can just take this as an exercise, because this actually generalizes that how to calculate the number of homomorphisms between groups of this form. Because ultimately the all finite abelian groups are decomposable into this particular notion, or in this some sense. Is it clear? Okay, so let me just think of something interesting if I should be talking about. Okay, let's do one important question and then we are good to go. So let me just write out the question and I'm then resuming the video. Okay, so this is the question. So let G be a cyclic group of order 8, and let H be a cyclic group of 5 objects. Which of the following are necessarily true? Number 1, there exists no non-trivial homomorphisms. There exists no injective homomorphisms from G to H. There exists no surjective homomorphisms from G to H. And there exist more than 20 different group homomorphisms from G to H. Now, obviously, please pause the video and try the question on your own, and we are moving on to the solutions. Now, the first thing which you can try and observe in this particular context is that what does it mean for there to be a surjective homomorphism? Now, recall that if phi from G to G prime is injective, okay, so surjective I'm coming, so it's injective, then we know that the kernel of phi is the trivial group 1. Hence, G is isomorphic to a subgroup of G prime. I hope you're getting the point. So for injective homomorphisms, you need to check that is there a subgroup of the codomain group which is isomorphic to G. And for surjective homomorphism, obviously you need to find, you need to check whether there is a homomorphism which maps the group completely to the codomain group. So let's check out the solution. The first thing which you can observe is the following. So we are working in S5. So for phi to be an injective homomorphism from G to S5, obviously we must have a cyclic group of order 8 in S5. Okay, that is obviously what you require, right? But, so again, this is a very easy exercise. There does not exist an element of order 8 in S5, because we will never be able to account for a partition of 5 such that the LCM of the elements in the partition come out to be 8. Okay, so which implies there does not exist a cyclic subgroup of S5 of order 8, and hence there does not exist an injective homomorphism from G to H. So option B is correct. What about option C? If phi from the cyclic group of order 8 to S5 is surjective homomorphism, then obviously what do you have? Then phi of C8 must be exactly equal to S5, but phi of C8, so image of a cyclic group is cyclic, while S5 is not cyclic, right? It's obviously not cyclic. Fine. So therefore this is also not possible, and hence it's true. Finally, number D. So here we need to check for all the possible number of homomorphisms. So firstly, let us do the algorithm again. So let K1 be the normal subgroup, let's say 1. So I can think of G to be generated by A, for example, or you can just work with okay, so what I can do is, yeah, so let's take the additive notation. So 0, because we know that every finite cyclic group is isomorphic to Zn. So here G is actually isomorphic to Z8, and every subgroup will be normal. So let K2 be the subgroup which is isomorphic, as an isomorphic copy I'm talking about. So Z2, K3, you can take it to be, so what are the divisors of 8? It's just 2, 4 and 8 itself. So it's Z4, and K4 is the whole group Z8. So therefore you have G1 to be the whole group G, you have G2 to be Z8 mod Z2, and so it will come out to be Z4. Then you have G3 to be Z8 mod Z4, which comes out to be Z2, and finally you have G4 to be just 1. Okay, now what do I have here? So now we have already proved that there is no injective homomorphism, so K1 will obviously not be a case. So G1 does not account for a homomorphism. So this is exactly the case, that there is no injective homomorphism. What about G2? So is there a subgroup of S5 which is isomorphic to Z4? So obviously, right, you can consider elements whose order is 4, right? So what are the number of elements of order 4 in S5? So what are the elements? What are the possible elements of order 4? So it's only 4 and 1. So this is the only possible cyclic decomposition, right? Is there any other possibility? No, because for the LCM to be 4, you need to have 4 at least, otherwise it won't be possible. So therefore so these account for the number of elements. What should be? So it should be 5 factorial by 4, which is 24, and what is the order of the automorphism group of Z4? So it should be phi of 4, which is 2. So we already got more than 20 more than 20 homomorphisms, right? Yeah, so we already got more than 20 homomorphisms, isn't it? So number of, did I do it correctly? Number of elements of order 4 in S4, did I do it correctly? No, I'm sorry. So this is 4 will as 4, so this is 30, I'm sorry. So number of homomorphisms equal to, so therefore what are the number of subgroups of order 4? Number of subgroups of order 4 is equal to 30 by phi of 4, which is 2, so it just comes out to be 15. right? So therefore number of homomorphisms here should be 15 times the cardinality of the automorphism group of Z4, which is again 30. So we already accounted for more than 20 homomorphisms, and then so hence option D must be true as well. So this is the way you usually talk about things in the following sense. I have already given a lot of exercises in this particular lecture. The final few exercises I would like to give, and I obviously want every viewer to dedicatedly solve each of these exercises, and the exercise is as follows. That is, a group G is abelian if and only if phi from G to G given by phi of x equal to x inverse is an automorphism. I would like to give one more exercise. Okay, so this is one. Number 2, prove that every let me think of an exercise. Prove that every group of order greater than 2. Okay, so this doesn't seem to be a good language. Let G be a group. Prove that if order of G is greater than 2, then G admits a non-trivial automorphism. Fine. So this is the end of this particular lecture. It's already a 52 minutes long lecture. So I'm ending this particular lecture here itself. I might be taking one more lecture talking about the finite abelian groups and their decomposition. That will be the final lecture of this particular course. After that, we will take probably 3 lectures on problem solving in group theory. Okay, so meet you guys in the next lecture.